Section 10.5 Changes of State. The states and properties of gases, liquids, and solids depend on the type of attractive forces between their particles. Matter undergoes a change of state when it is converted from one state to another state. When a solid goes directly into a gas, it sublimes. When a gas is directly converted into a solid, it deposits. That's deposition. When a solid goes to a liquid, it melts. When a liquid goes to a solid, it freezes. When a gas goes to a liquid, it condenses. And when a liquid goes to a gas, it vaporizes. These are changes of state. Melting and freezing. When heat is added to a solid, the particles move faster. At a temperature called the melting point, enough energy is absorbed to overcome the attractive forces such as ionic or dipole-dipole forces that hold the particles together in the solid, and the rigid solid structure changes to a random association of particles in the liquid. The substance is melting, changing from a solid to a liquid. During a change in state, the temperature of a substance remains constant. If the temperature of the liquid is lowered, the reverse process takes place. Heat is removed from the liquid, which causes the particles to move slower. Eventually, the attractive forces between the particles are sufficient to form a solid. The substance is in the process of freezing, changing from a liquid to a solid at the freezing point, which is the same temperature as the melting point. Every substance has its own freezing or melting point. Solid water, ice, melts at 0 degrees when heat is added and freezes at 0 degrees when heat is removed. Gold melts at 1064 degrees Celsius when heat is added and freezes at 1064 degrees Celsius when heat is removed. During a change of state, the temperature of a substance remains constant. Suppose we have a glass containing ice and water. The ice melts when heat is added at 0 degrees Celsius, forming more liquid. When heat is removed at 0 degrees Celsius, the liquid water freezes, forming more solid. The process of melting requires heat. It's endothermic. The process of freezing releases heat. It's exothermic. Melting and freezing are reversible at 0 degrees Celsius. Melting and freezing are reversible processes. Heat of fusion. During melting, the heat of fusion is the energy that must be added to convert exactly 1 gram of solid to a liquid at the melting point. For example, 334 joules of heat is needed to melt exactly 1 gram of ice to it at its melting point, 0 degrees Celsius. Water solid plus 334 joules per gram yields liquid water, and that's endothermic. The heat of fusion, 334 joules per gram, is also the quantity of heat that must be removed to freeze 1 gram of water at its freezing point. So liquid water goes to solid water with a giving up 334 joules per gram at exothermic. Water is sometimes sprayed in fruit orchards during sub-freezing weather. If the air temperature drops to 0 degrees Celsius, the water begins to freeze. Because heat is released as the water molecules form solid ice, the air warms above 0 degrees and protects the fruit. Heat of fusion for water. 334 joules per 1 gram of water and 1 gram of water per 334 joules. The heat of fusion can be used as a conversion factor in calculations. For example, to determine the heat needed to melt a sample of ice, the mass of ice in grams is multiplied by the heat of fusion. Because the temperature remains constant as long as the ice is melting, there is no temperature change given in the calculation as shown in sample problem 10.8. Calculating heat to melt or freeze water. Heat equals the mass times the heat of fusion. So joules equals grams times 334 joules per gram. Grams cancel, and so the heat will be equal to the heat of fusion. Evaporation, boiling, and condensation. Water in a mud puddle disappears, unwrapped food dries out, and clothes hung out on a clothesline dry. Evaporation is taking place as molecules of liquid water with sufficient energy escape from the liquid surface to enter the gas phase. The loss of the hot molecules removes heat, which cools the remaining liquid water. At higher temperatures, more and more water gains sufficient energy to evaporate. At the boiling point, all the molecules within the liquid have enough energy to overcome the attractive forces and become a gas. We observe the boiling of a liquid such as water as gas bubbles form throughout the liquid, rise to the surface, and escape. Figure 10.4. Evaporation occurs at the surface of a liquid. Boiling occurs as bubbles of gas form throughout the liquid. When heat is removed from a gas, a reverse process takes place. In condensation, water vapor is converted back into liquid as the water molecules lose kinetic energy and slow down. Condensation occurs at the same temperature as boiling, but differ because heat is removed. You have noticed that the condensation occurs when you take a hot shower and the water vapor forms water droplets on the mirror. Because the substances lose heat as it condenses, its surroundings become warmer. That's why when a rainstorm is approaching, we may notice a warming of the air as gaseous water molecules condense to rain. Heat of vaporization. The heat of vaporization is the energy that must be added to convert exactly 1 gram of liquid to gas at its boiling point. For water, 2,260 joules is needed to convert 1 gram of water to water vapor at 100 degrees. So water liquid plus 2,260 joules per gram yields gaseous water, which is endothermic. This is also the case of the amount of heat released when 1 gram of water vapor gas changes to a liquid at 100 degrees Celsius. Therefore, 2,260 joules per gram is also the heat of condensation of water. Gaseous water converts into liquid water plus a release of 2,260 joules per gram. That's exothermic. Just as substances have different melting and boiling points, they also have different heats of fusion and vaporization. As seen in figure 10.5, the heats of vaporization are larger than the heats of fusion. Water has a heat of fusion of 334 joules per gram. Water has a heat of vaporization of 2,260 joules per gram. The heat of vaporization can be used as a conversion factor in calculations. 2,260 joules for 1 gram of water and 1 gram of water for 2,260 joules. To determine the heat needed to boil a sample of water, the mass in grams is multiplied by the heat of vaporization. Because the temperature remains constant as long as the water is boiling, there is no temperature change given in the calculation, as shown in sample problem 10.9. Calculating the heat to vaporize or condense water. Heat equals mass times the heat of vaporization. Joules equals grams times 2,260 joules per gram, and grams cancel. Heating and cooling curves. All the changes of state during the heating of a solid can be illustrated visually. On a heating curve, the temperature is shown on the vertical axis and the addition of heat is shown on the horizontal axis. Steps on a heating curve. The first diagonal line indicates a warming of the solid if heat is added. When the melting temperature is reached, a horizontal line or plateau indicates the solid is melting. As melting takes place, the solid is changing to a liquid without any change in temperature. Once all of the particles are in the liquid state, heat that is added will increase the temperature of the liquid. This increase in temperature is the diagonal line from the melting point to the boiling point temperature. Once the liquid reaches the boiling point, a horizontal line indicates that the temperature remains constant as the liquid changes to gas. Because the heat of vaporization is greater than the heat of fusion, a horizontal line at the boiling point is longer than the line at the melting point. Once all the liquid becomes gas, adding more heat increases the temperature of the gas. Steps on a cooling curve. A cooling curve is a diagram of the cooling process, which is the reverse of the heating curve. In the diagram, the temperature is plotted on the vertical axis and the removal of heat is plotted on the horizontal axis. Initially, a diagonal line to the boiling condensation point is drawn to show that the heat is removed from a substance, cooling the gas until it begins to condense. A horizontal line or plateau is drawn at the condensation point, the same as the boiling point, to indicate the change of state as the gas condenses to form a liquid. After all the gas is changed into a liquid, further cooling lowers the temperature. The decrease in temperature is shown as a diagonal line from the condensation point temperature to the freezing point temperature. At the freezing point, another horizontal line indicates that the liquid is changing to a solid at the freezing point temperature. Once all the substance is frozen, a loss of more heat decreases the temperature of the solid below its freezing point, which is shown in the diagonal line below its freezing point. Combining energy calculations. Up to now, we've calculated one step in heating or cooling curve. However, a problem may require a combination of steps in which a substance may change state, and then new state undergoes a temperature change followed by another change of state. When the temperature of a substance is changing and not in state, we need to use the heat equation, which includes delta T. The heat in joules equals the mass in grams times the temperature change times the specific heat. The heat is calculated for each step separately, and the results are added up together to give the total energy as seen in sample problem 10.10. Sublimation. In a process called sublimation, the particles on the surface of a solid change directly to a gas with no temperature change and without going through the liquid state. In the reverse process of sublimation, called deposition, gas particles will change directly to a solid. For example, dry ice, which is a solid carbon dioxide, undergoes sublimation at negative 78 Celsius. It is called dry because it does not form a liquid as it warms. In extremely cold areas, snow does not melt, it sublimes directly to water vapor. In a frost-free refrigerator, the water on the ice in the ice on the walls of the freezer and the frozen food sublimes when warm air is circulated through the compartment during the defrost cycle. When frozen foods are left in the freezer for a long time, so much water sublimes on the food, especially meats, that they become dry and shrunken, a condition called freezer burn. Deposition occurs in a freezer when water vapor forms ice crystals on the surface of freezer bags and frozen foods. Freeze-dried foods prepared by sublimation are convenient for long-term storage and for camping and hiking. A food that has been frozen and placed in a vacuum changer where it dries as the ice sublimes. The dried food retains all of its nutritional value and needs only water to be edible. The food that is freeze-dried does not need refrigeration because bacteria cannot grow without water.